Good morning, everyone. Hope you are all doing fine. This video, we will continue what we have already started in the other two parts, in the first two parts of aldehydes and ketones. If you remember, in the first video, part one of aldehydes and ketones, we discussed their structure, their nomenclature, their methods of synthesis, and their physical characters. And then in the second part of aldehydes and ketones, the video dealt with the first two types of reactions of aldehydes and ketones. And these were the nucleophilic addition reactions. And we said that these are three examples. We explained the addition of Grignard, the addition of alcohol, giving the acetals and the hemiacetals, and the ketals and hemiketals, and the cyclic acetals and the cyclic ketals as a protective method of aldehydes and ketones. The third nucleophilic addition was the hydrocyanic acid, where we added cyano group to the carbonyl carbon, giving the cyanohydrins, which were of great use because they can be hydrolyzed into acids and reduced into amines. Then we dealt with nucleophilic addition followed by elimination of molecule of water, which is the condensation types of reactions. In the condensation reactions, we dealt with the reaction of carbonyl compounds with amines, whether primary amines, secondary amines, or amine derivatives. Then today, we will deal in this video with the second two types of reactions, which are the reactions due to acidity of alpha hydrogen, and the second type is the oxidation reduction reactions. So let's start with the third type of reactions, which is the reaction of carbonyl compounds due to the presence of alpha acidic hydrogen. If you have a carbonyl group and you have alpha to it, a hydrogen, this hydrogen is regarded as an acidic hydrogen. What is the definition of an acid? It's a compound that is capable of liberating a proton. So if this hydrogen is abstracted by a base and leaves the molecule as a proton, it will leave the carbon that it was attached to as a negatively charged carbon. This negative charge can be stabilized by resonance with the carbonyl carbon. Accordingly, this compound is a stable compound, and this reaction is a feasible reaction. You can actually abstract this proton using a base. So this is why the alpha hydrogen to the carbonyl is an acidic proton. How can we utilize this? We have three types of reaction. First one is the aldol reaction. The second type is the halogenation. And the third type is the Mannich reaction. Let's discuss each separately. Let's first start with the aldol condensation reaction. What is an aldol reaction? The aldol reaction relies on using a carbonyl compound that has an alpha hydrogen. As we mentioned, this alpha hydrogen is acidic. Accordingly, it can be abstracted by a base, leaving a negative charge on the carbon, which, as we said, is stabilized by resonance. As we always say in any organic chemistry reaction, you do not have one molecule in your container of the starting material. You have several molecules. So some of these molecules are still unreacted. They still exist in the aldehydic, not in the enol form. So this negative charge can attack the carbonyl of another molecule, breaking the pi bond. Always start drawing from the carbonyl compound that was not attacked by the base. the one that has all its alpha protons. So you start with the CH3, and then it is attached to a carbon that is now singly bonded to the oxygen and attached to the hydrogen, and it was attacked by the CH2, so now it's attached to this CH2, and then the aldehydic group as it is. The proton that was abstracted at the beginning of this reaction will attach itself to the negatively charged oxygen, giving the alcoholic compound. In case of aliphatic compounds, this is the end of the aldol reaction, unless if we heat in presence of dilute acids. This results into a condensation reaction where a molecule of water is lost, giving the alkene compound. It gives an alpha-beta unsaturated aldehyde or alpha-beta unsaturated ketone. So this reaction, the final step where you perform the condensation, where you remove the molecule of water, it does not take place spontaneously. You have to use a dilute acid and warm your reaction. Otherwise, this reaction will not proceed. However, if you have started with an aromatic compound, such as acetophenone, for example, this is an aromatic compound that has an alpha acidic hydrogen. Here is your carbonyl compound. This is a benzene ring to classify this as an aromatic ketonic compound. And then alpha to the carbonyl, you have a carbon that is carrying hydrogens. If you add a base, you will abstract the alpha proton, leaving a negative charge on the carbon, which is stabilized, as we said, by resonance. Again, as we said, you do not have only one molecule of your compound, you have several molecules that have not reacted yet. And accordingly, their carbonyl is carrying a partial positive charge, so the negatively charged carbon will attack them. As we said, you start from the carbonyl compound that was not attacked by the base. Now the carbon is attached, singly bonded to an oxygen. This is the carbon that we are drawing. It's attached to a benzene, oxygen, CH3, so a benzene, oxygen, CH3, and now it's attached to an additional CH2 that it has been attacked with. So now we have the CH2 and then the carbonyl and the benzene ring. As we said, the proton will attach itself, giving the alcoholic compound. Now, if you remove this hydrogen with this OH as to remove a molecule of water, you will produce a double bond between these two carbons. This double bond is now in conjugation with the benzene ring. You have here double, single, double. It's in conjugation with the benzene ring and in conjugation with this ketonic compound. So you have here double, single, double, single, double, single, double, single, double, single, and double, single, and so on. It allows the conjugation to continue between the two systems. And accordingly, this dehydration is spontaneous. It takes place without adding an acid and without warming. It takes place spontaneously, even if we do not interfere and we do not do anything. So the base usually used during aldol condensations is dilute sodium hydroxide, which is a 10% sodium hydroxide. So if we say 10% or we say dilute sodium hydroxide, then we are probably dealing with aldol condensation. Remember that this reaction can be a cross aldol, which means that you can use two different molecules, not just one molecule. How can you do this? You can use the acetaldehyde as the aldehyde that has an alpha acidic hydrogen together with something like formaldehyde or benzaldehyde. This is an aldehyde that does not contain an alpha acidic hydrogen. First of all, the base will abstract the proton, putting a negative charge on this carbon, and it will attack the carbonyl of the formaldehyde, giving this as a product. Again, you will lose a molecule of water if you warm in presence of a dilute acid, giving the alpha-beta unsaturated aldehydic compound as a product. This is the aldol condensation. We have one very important application for aldol condensations, which is the nitroalkanes. The nitroalkanes are compound that has the nitro group. This reaction will be discussed in full details when we deal with the nitrogenous compounds. These compounds again has an alpha acidic hydrogen, which if they lose will be stabilized by resonance. Accordingly, this hydrogen can be abstracted by a base. So if we add a base, it will abstract this proton, putting a negative charge on the alpha carbon to the nitro group. And accordingly, if you add something like benzaldehyde, any carbonyl compound, the negative charge will attack the partially positive carbonyl carbon, giving the condensation, giving the product of the addition of the first step, followed by condensation that will take place spontaneously due to the presence of a benzene ring. So this is the aldol condensation, and this is how it proceeds. The second reaction is the halogenation reaction. How does this reaction proceed? Again, it depends on the presence of an alpha acidic hydrogen that will be removed and a halogen will be introduced in its place. This halogen can be the chloro, the bromo, or the iodo. Okay? How does this reaction proceed? How is it performed? What is the mechanism of such a reaction? It depends on your conditions. You can perform the reaction in acid medium and you can perform it in alkaline medium. Let's first discuss the acid medium. In case of acid medium, you have a carbonyl and you have a carbon attached to it that is carrying an alpha hydrogen. You add an acid medium, so you protonate the oxygen, breaking the double bond between the carbon and the oxygen. Now your carbon is carrying a positive charge and it can be stabilized by removal of the alpha hydrogen, giving the enol form. So this is how your reaction starts. It starts by protonation of the oxygen by the acidic medium that you have introduced. Afterwards, this double bond attacks the halogen you are using, giving the halogen on the alpha hydrogen. And then you have a positive charge on your carbon attached to the OH. Accordingly, the ketone reforms to neutralize this positive charge. So now let's repeat this mechanism. As we said, you have a carbonyl attached to a carbon which is carrying an alpha hydrogen. You protonate using acid medium. So the double bond breaks to stabilize the oxygen, putting the positive charge on the carbon. Afterwards, the alpha acidic hydrogen leaves to neutralize the positive charge on the carbon. Then you have the halogen. The double bond will break in the direction of the alpha carbon, which will attack the halogen attaching the halogen to the alpha carbon, and now you have the carbonyl, or what used to be the carbonyl, which is now attached to the OH, carrying a positive charge. So the proton leaves the molecule to reform the carbonyl compound and neutralize the positive charge on the carbon. This is how the reaction proceeds. It ends up into this step. It's a monohalogenation. This is the first character of this reaction. It cannot be continued. You cannot do a double or a triple halogenation, because your carbon is now attached to a halogen, so it's reluctant to continue the same reaction. So this is one property. The second property is that it's a non-terminal halogenation. What does that mean? It means that if you have the option between this carbon and that carbon, if you have an option between this CH3 or this CH2, the halogen will choose this non-terminal carbon because it proceeds through a double bond formation. So accordingly, as we said, in case of alkenes, if you do not remember this character, please refer to the video of alkenes. You will find that double bonds, according to Side's rule, prefer to be non-terminal, prefer to be more substituted. So that's why this reaction gives the halogen on the non-terminal carbon. If it has more than one choice, whether terminal or non-terminal, it will choose the non-terminal carbon, and it's a monohalogenation reaction. It will not give a second halogenation step. Okay, so this is the acid catalyzed halogenation of carbonyl compounds. Let's look at the base catalyzed reactions. In case of base catalyzed reaction, you have the carbonyl compound and you have again an alpha acidic hydrogen. As we said, whether it's an acidic mechanism or a basic mechanism, they both rely on the presence of an alpha acidic hydrogen. So you have the alpha acidic hydrogen, you add a base. The base will abstract the alpha acidic hydrogen. You do not need to perform the enol formation or the protonation, like in case of the acid catalyzed reaction. Now you have a carbon carrying a negative charge and you have a halogen in your medium, so the carbon carrying the negative charge will attack the halogen and giving the halogenated compound. In this case, your halogenation will be a multiple halogenation, which means that if you have another hydrogen on this carbon, again the base will abstract this hydrogen, putting a negative charge on the carbon and attacking another molecule of the halogen. And then a third halogenation. This is the first character, so it is a multiple halogenation. The second character is that it's a terminal halogenation. It prefers to halogenate a terminal carbon rather than a non-terminal carbon. And the final product is not even this product. The final product is that your base will then attack the carbonyl, will act as a nucleophile and attack your carbonyl, breaking the double bond between the carbon and the oxygen, and then the carbonyl reforms, throwing away what we call iodoform or halo form, and it gives you the carbonyl in the form of an acid. A proton exchange takes place where the hydrogen moves to the halo form, leaving the sodium salt of the acid. This is how the base catalyzed reaction proceeds. So let's compare the acid catalyzed and the base catalyzed. you have your compound. For this reaction to proceed, you need to have a CH3 attached to a carbonyl group. If we run the acid-base halogenation, we will have a mono non-terminal halogenation. So it's a mono halogenation, and it's non-terminal, prefers to be in the middle of the compound, and finally the final product is what we have just drawn. However, if we use the base catalyzed halogenation, first of all, it's a multiple halogenation. Secondly, it's a non-terminal. Your attack will be on the peripheral alkyl group, as you can see. And finally, the final product is a decomposition product where you will get the halo form plus the sodium salt of the acid. You break your compound right here. This gives your halo form, and this gives the acid part of your product. So this is how halogenation proceeds. Let's just discuss halo form for a second. For halo form to proceed, you have got to have one of two moieties. It's either a methyl attached to a carbonyl, or it's an OH attached to a carbon that is carrying a hydrogen and another methyl. If you do not see this structure or that structure, no matter what is attached to the other side, you cannot perform halo form. How can the alcoholic compound give the halo form? The first step, using the iodine, oxidizes this compound, this secondary alcoholic group, into the carbonyl compound, into the ketone. And then the regular halo form proceeds like you used to do. As we said, you first halogenate for 3 times the terminal carbon, and then you attack using your hydroxyl group and release your halo form and the sodium salt of your acid. So this is what halo form is and how it proceeds and the requirements needed for halo form. One last thing for the reaction of halo form, which is why does the acid reaction give a monohalogenated compound while the base reaction gives a multiple halogenated compound. Let's first look at the acid. As we said, the first step involves the protonation of the oxygen. For such a reaction to proceed, you have to have a full lone pair of electrons on the oxygen that are not attracted towards any other atoms for the protonation to take place. So this is the molecule that is preferred by the proton or by the acid medium to be protonated. However, when you run the first halogenation, now your proton has 2 choices. It can choose to halogenate the starting material, which does not have a halogen in it, and it can choose to protonate the compound, the product that has the halogen in it. If you look at this compound, the halogen is an electron withdrawing group. Accordingly, it's attracting the electrons from the oxygen towards the halogen. And accordingly, the lone pair of electrons are not that much available to be protonated. And that's why one halogenation takes place and it does not proceed for a second halogenation. However, in case of alkaline medium, you abstract this proton and you put a halogen in its place. If you are looking at the second proton, The first proton was acidic because its removal will be stabilized by resonance. The second proton, if you remove it, the negative charge present will be stabilized first by the negative inductive effect of the halogen and second by the resonance with the carbonyl group. So accordingly, you end up removing the second and the third halogen because of this stabilization of the halogen, of the negative induction of the halogen, and that's why you get a multiple halogenation. Finally, the third type of reactions that involves the alpha acidic hydrogen is the Mannich reaction. What is the Mannich reaction? In this reaction, you react formaldehyde with a secondary amine in presence of an inorganic acid, and then you add a compound that has an alpha acidic hydrogen. How does this reaction proceed? First of all, you protonate the formaldehyde and accordingly you break the double bond between the carbon and the oxygen, leaving a positive charge on the carbon. You have in your medium the secondary amine that can react or attack the carbon that is carrying a positive charge. It's a nucleophile that can attack this carbon. So now you have the CH2 of the formaldehyde and the OH, and you have the amine now attached to it. You still have acid medium, so another protonation takes place, removing a molecule of water, giving your reagent in the form of a positively charged compound. When the molecule of water leaves as a neutron molecule, it leaves a positive charge on the carbon that it was attached to. Remember that this positive charge is stabilized by resonance with the amino group. This is how the reagent is formed at the beginning. The attacking agent is formed at the beginning. The next step is that you add a compound that has an alpha acidic hydrogen. An example of that is any carbonyl compound having an alpha acidic hydrogen. Again, you are using an inorganic medium, so you protonate the carbonyl, breaking the double bond and performing the enol tautomerism. Let me draw this on several steps. First, you protonate. Then you break the double bond, putting a positive charge on this carbon. A proton leaves, creating the enol form to neutralize the positive charge on the carbon. Now you have your reagent, which is this and that, in resonance with each other. Sometimes the nitrogen is carrying the positive charge and sometimes the carbon is carrying the positive charge. The double bond of the enol compound, the carbonyl compound reforms, breaking the enol, which will attack the carbon of the reagent. So now you have the carbonyl. This is your carbonyl. It's attached to a CH2, which is now attached to the CH2 of the formaldehyde, and finally the amine. Whatever you had on this side will just keep moving with you. So what is the end product of this reaction? The end product of this reaction is that you started with a carbonyl compound that had an alpha acidic hydrogen. You added formaldehyde and a secondary amine in presence of an inorganic acid. The final product is that you remove one of these alpha acidic hydrogens. you add the CH2 of the formalin in its place, and then you attach the nitrogen of the secondary amine to your product. So this is the end product of Mannich reaction. So now if we look at the organized slides for this part, we will find that first of all, we dealt with why the alpha hydrogen to a carbonyl compound is an acidic hydrogen because of the resonance. And then we dealt with the reactions. We started with the aldol condensation. As we said, it will stop at the OH if we do not warm the reaction in presence of an dilute acid. The first step is that the base abstracts your proton, giving the negative charge, which is stabilized by resonance. The second step is the attack of the negatively charged carbon on another molecule of your aldehyde, giving your hydroxy compound as a product. And then, as we said, if we warm this product in presence of a dilute acid, you will end up losing a molecule of water, giving the alpha beta unsaturated carbonyl compounds. We said that you can perform this on any compound that has an alpha acidic hydrogen, whether aldehyde or ketone. So this is another example. And as we said, if you have a benzene ring attached to your carbonyl, the dehydration is a spontaneous reaction because the double bond is in conjugation with the benzene rings. And we said that the application of this reaction is reactions of nitroalkanes with different aldehydic compounds. Then the second reaction was the halogenation, where we have an alpha acidic hydrogen that will be replaced by a halogen. And we said that this reaction can proceed either in acid medium or in alkaline medium, and they differ totally from each other in how they proceed and in the final product obtained. First of all, when we deal with the acid catalyzed reaction, as we said, the first step will be the protonation, giving the enol form. And then this enol form will attack the halogen to put it on the alpha carbon in place of the alpha acidic hydrogen, giving your final product as a monohalogenated non-terminal compound. In case of base catalyzed, as we said, the base will abstract the proton first, and then, as we said, this negative charge is stabilized by resonance, and the negative charge will attack the halogen, putting a halogen on the carbon alpha to the carbonyl group. If we have additional hydrogens on this carbon, they are more acidic now because of the electron withdrawing capability of the halogen, so multiple halogenation will take place. The multiple halogenation takes place in case of haloform, and as we said, the requirement is that you need a carbonyl attached to the CH3 or a secondary alcoholic group attached to a CH3. Accordingly, acetaldehyde is the only aldehyde that can perform this reaction, and ethyl alcohol is the only primary alcohol that can perform this reaction. Okay, lactic acid gives this reaction, but you need to use a 30% sodium hydroxide. All secondary alcohols, if they have a methyl group attached to their carbon, which is carrying the OH, will give a positive iodoform test. The mechanism of this reaction is, if you are actually starting with an alcohol, first step will be oxidation to the carbonyl compound, and then you will have the halogenation, the multiple halogenation, and then the cleavage into the haloform. As we said, the halogenation will be first the hydroxyl group will abstract a proton, and then the negative charge will attack the halogen, introducing a first halogen atom, and then this will repeat until we introduce all three halogen atoms. And then the hydroxyl group will start acting as a nucleophile. It was acting as a base before abstracting the acidic protons. Now, since there are no more acidic protons, it will start acting as a nucleophile and it will attack the carbonyl group, breaking the double bond, which will reform, throwing away the halo form. The halo form is in the form of a salt, while the acid is in the form of the free acid, and this is not acceptable because the acid is stronger than the halo form in its acidity. So a proton exchange takes place, giving the halo form, which is, if your halogen is an iodine, called iodoform, and we have all seen the yellow precipitate of the iodoform in the lab, together with the sodium salt of the acid. This is the comparison that we have dealt with in case of acid medium and alkaline medium. As we said, in acid medium you get a middle halogenation, monohalogenation, and the product is what you have already obtained in the first step. However, in case of alkaline medium, you will obtain terminal halogenation, not middle halogenation. You will get multiple halogenation, and your final product is the haloform and the sodium salt of the acid. Finally, the Mannich reaction, as we said, you use a compound that has an alpha acidic hydrogen. You add to it formaldehyde and a secondary amine in presence of inorganic acid. In the end product is that you remove one of these hydrogens and you add in their place the formaldehyde CH2 part and the secondary amine. This is the mechanism that we have discussed in full details. Now we will deal with a new type of reactions that aldehydes can perform if they do not have an alpha acidic hydrogen. If you have something like formaldehyde and then you add the conditions of aldol to it, which is sodium hydroxide. However, you just need to use concentrated. In case of aldol condensation, you were using dilute sodium hydroxide. Here you will have to use concentrated sodium hydroxide. The end product is oxidation reduction reaction. One molecule of the formaldehyde will be converted into the formic acid and the other molecule will be converted into methanol. So one molecule got oxidized to the acid and the second molecule got reduced to the alcohol. This is what we call Cannizzaro reaction. Remember that the acid will be in the form of the sodium salt. You are using an alkaline medium, so your product will be in the form of a sodium salt. Let's perform the same reaction on another aldehyde that does not contain an alpha acidic hydrogen, like benzaldehyde. Again, if you use concentrated sodium hydroxide, which is 30% sodium hydroxide, you will have one of the molecules oxidized to the acid and the other molecule reduced to the alcohol. What is the mechanism of this reaction? The mechanism of this reaction is that you have a carbonyl that is carrying a partial positive charge and you have a hydroxyl group from the sodium hydroxide that is carrying a negative charge. Accordingly, the hydroxyl group will attack the carbonyl, breaking the double bond. The double bond reforms, throwing away a hydride, which is not a very common leaving group. However, the reaction conditions will throw away a hydride molecule, giving the acid. The hydride molecule will attack another molecule of the aldehyde. It's now acting as a nucleophile since it's carrying a negative charge, breaking the double bond, and then the compound will attach itself to any proton from the medium, giving the alcohol. Notice that if you have more than one type of aldehydes, the attack of the OH will be on the carbonyl of the aldehyde that has the more positive charge. What does that mean? It means that if you are actually starting with benzaldehyde, together with formaldehyde, and you are using conditions of Cannizzaro reaction. The hydroxyl group here has two choices. It has the choice to attack this carbonyl and the choice to attack the other carbonyl. If you remember, in part 1 of aldehydes and ketones, we said that the carbonyl of aliphatic aldehydes has a more positive charge and accordingly is more reactive than the carbonyl of aromatic compounds, and this is because of the donation power of the benzene ring. So the hydroxyl group will choose the more reactive carbonyl. Throwing away a hydride molecule which will attack the benzaldehyde carbonyl, giving the alcohol. So the aldehyde that is more reactive is the one that will be converted into the acid, and the less reactive aldehyde will be converted into the alcohol. In other words, the aldehyde that has the more positive charge will be oxidized, while the aldehyde that has a less partial positive charge on its carbonyl will be reduced. Notice that the proton of the acid will move to the alcohol. This alcohol was carrying a negative charge, so a proton exchange will take place to give the stable alcoholic molecule and the sodium salt of the acid formed, because acids are more acidic than alcohols, so they can exist as salts. So as we said, Cannizzaro reaction is a self-oxidation reduction reaction where a molecule of an aldehyde, two molecules of an aldehyde is reacted with sodium hydroxide, concentrated sodium hydroxide, and one of these molecules is reduced into the alcohol and the other one is oxidized into the acid, and it gives the sodium salt form of the acid. As we said, the mechanism starts with an attack of the hydroxyl group on the carbonyl, followed by breaking the double bond between the carbon and the oxygen. The double bond reforms, throwing a hydride that will attack another molecule of the aldehyde, giving the acid and the alcohol in the form of a salt. It's preferable that the acid would be in the form of the salt rather than the alcohol, so a proton exchange takes place, giving the salt of the acid and the free alcohol. As we said, if we perform a cross Cannizzaro where we actually use two different aldehydes, the hydroxyl group will choose the aldehyde whose carbonyl is more positive. In other words, it will choose the more reactive aldehyde to attack, and this is the aldehyde that will be converted into the acid. The other aldehyde will be converted into the alcohol. In other words, the more reactive aldehyde will be oxidized and the less reactive aldehyde will be reduced. One last reaction is cross-aldol, cross-Cannizzaro reaction, where we can actually use two molecules of an aldehyde. One contains an alpha-acidic hydrogen and the other does not. If we place these two molecules in an alkaline medium, the first choice will be that regular aldol. So aldol condensation will be performed on the aldehyde that contains the alpha-acidic hydrogen, and as long as it is having an alpha-acidic hydrogen, it will keep performing the aldol condensation. How does that proceed? You have the acetaldehyde in presence of the base. You abstract the first proton, and it will attack the aldehyde that does not contain the alpha-acidic hydrogen, putting a CH2OH on the CH2 carbon. So this CH2 now is attached to the CH, and this has been converted into an OH. This reaction will further proceed because you still have alpha acidic hydrogens. So you will have a negative charge on this carbon, and it will use it to attack another formaldehyde molecule. It still has an additional alpha acidic hydrogen, so the base will abstract it, putting a negative charge on this carbon, and it will use it to attack another formalin molecule. Now that all the alpha acidic hydrogens are used up, the sodium hydroxide will have no other choice than to act as a nucleophile. It now has two choices. It can choose between this carbonyl and that carbonyl. It will choose the more positive or the more reactive carbonyl, which is the formaldehyde. So it will attack formaldehyde, converting it into formic acid and giving a hydride molecule that will attack this carbonyl, giving what we call pentaerythral. So again, if we look at this reaction, as you can see, you have the acetaldehyde, the formaldehyde in presence of concentrated sodium hydroxide. First step will be a regular alveolar condensation between the acetaldehyde and the formaldehyde, and then you have the Cannizzaro step where you perform oxidation of the formaldehyde and reduction of the beta-erythritol part. The second type of reactions that does not involve the presence of an alpha acidic hydrogen. The first type was the Cannizzaro. The second type is the benzoin condensation. What is the benzoin condensation? You use two molecules of a formaldehyde. Of a benzaldehyde. You use two molecules of formaldehyde. You add cyanide group to this compound, and you end up with the benzoin product. This is the structure of your benzoin, where one of the molecules of the benzaldehyde, the carbonyl of which stayed as a carbonyl, while the other carbonyl of the second molecule was converted into an alcohol. How does this reaction proceed? It proceeds first, you have the first benzaldehyde molecule. It will be attacked by the cyano group, giving the cyanohydrin. It's preferable for this proton to move from the carbon to the oxygen, and I will show you now why. So a proton exchange takes place. And now the carbon is carrying the negative charge. Why is it preferable for the carbon to carry the negative charge than the oxygen, even though oxygen are more electronegative? Because now the negative charge has been moved to a carbon that is alpha to a benzene ring, and it's attached to a cyano group. What does that mean? It means that this negative charge is stabilized by resonance towards the cyano group and is stabilized by resonance towards the ring. While in case of the oxygen carrying the negative charge, the only stabilization was just an inductive effect of the cyano, no resonance, and the benzene was unable to help with the resonance. So this is why the negative charge moves to the carbon and leaves the oxygen. And this is why this reaction is specific only to benzaldehyde, so that the carbon that will be attacked will be able to carry the negative charge in place of the oxygen due to the stabilization of the benzene ring together with the cyano group. This molecule will attack another molecule of benzaldehyde. Remember that we have a carbon that is carrying a negative charge, and another molecule will have a carbonyl carrying a partial positive charge. So we will have an attack. Let's see how we will draw. Let's draw this benzene first. So this is the first benzene. What is it attached to? It's attached to a carbon that is now singly bonded to an oxygen and a hydrogen. So single bond oxygen and a hydrogen. And it will be attached to the carbon that was carrying the negative charge, and it will be attached to the cyano and hydroxyl group. So this is my carbon having an OH and a cyano group, and finally the benzene ring. So this is your product. How does this reaction proceed? It proceeds through first moving a proton exchange between this oxygen and this oxygen. Why is that? We need to move the negative charge from this oxygen, which is not stabilized by anything other than induction, to this oxygen, where it will be stabilized by resonance with the this system. Let's see how will this happen. If we move this proton here, now you have an OH and an H, and then you have a C carrying an oxygen, which is now carrying a negative charge since it gave away its proton, and the carbon is attached to a cyano and a benzene ring. This negative charge can be given to the carbon to form a bond, and the cyano can leave as cyanide molecule, as a cyanide molecule, giving our benzoin product. Notice that the cyano was introduced and then removed without appearing in your final product. This is the definition of a catalyst. It's a molecule. A catalyst is a molecule that is needed during the reaction, but it's not a part of your final product. It enters the reaction and then it leaves the reaction before it ends. This is a catalyst, and accordingly you need very small amounts of the cyano group. You need trace amounts of the cyano. If you can actually use one molecule, it will be highly preferable. However, we can never use a one molecule of any compound. Even if we use one drop of the compound, still it contains millions and millions of molecules. So this is how the benzoin proceeds. This compound has an important application, which is that it can be oxidized into what is called benzyl compound. So if this is your benzoin, if you reacted with nitric acid, you will oxidize this secondary alcoholic group and you will have two carbonyls in between two benzene rings. Why is this important? Because it performs another important reaction, which is the benzyl-benzylic rearrangement. How does this reaction proceed? You take this compound and you add a base, strong base, to your compound. What will take place is some sort of an internal Cannizzaro reaction. You have two carbonyls. So one of them will be oxidized into the acid and the other one will be reduced into the alcohol. How does that take place? First, you will attack the first carbonyl. By the way, it doesn't matter which one you will start with, they are identical. So now you have an OH attached to the carbon that you have attacked, and as an oxygen that is now carrying a negative charge. The double bond reforms, and what happens here is that you have a phenide shift, a full shift of the phenyl group with its electrons. So let's start drawing from this side. You have a benzene. This benzene is attached to this carbonyl, which is now not a carbonyl because you attacked it with a phenyl group. So you broke the double bond and it's carrying an oxygen having a negative charge. And then it is attached to this carbon that has been converted to a carboxylic acid. Again, as we mentioned, you have now the salt of an alcohol and a full acid. So you have to have proton exchange between this hydrogen. It will move to this oxygen and you will get the benzylic acid. What is the benzylic acid? It's a product of an oxidation reduction reaction, an internal Cannizzaro performed on benzyl molecule. If you need to facilitate this reaction, you can remove the benzene and just put a phenyl in its place. How can this be drawn? You can just have this as the benzyl to facilitate it. You attack by the alkaline medium. You reform the double bond and you perform the phenide shift. And then you run the proton exchange. This is to make things easier. So this is the benzylic rearrangement. As we said, this reaction first starts by the benzene, where we use 2 molecules of benzaldehyde in presence of a cyano group as a catalyst. Remember that it's a catalyst. It gives the benzene. How does it proceed? It proceeds through first attack of the cyano on the carbonyl of the benzaldehyde, giving something like the cyanohydrin. However, it does not abstract a proton from the medium, it abstracts the proton from the carbon that used to be a carbonyl. Why is that? Because this carbon can carry a negative charge due to resonance with the cyano group and the benzene ring. Then the negative charge will attack another molecule, attaching a C singly bonded to an oxygen and a hydrogen and a benzene ring to your original carbon. Again, as we said, a proton exchange takes place because this oxygen can carry a negative charge better than this one because, as we said, it will reform the double bond, removing the cyano group, giving the benzoin compound, which can be oxidized using nitric acid to give the benzyl, which will perform rearrangement in presence of potassium hydroxide to give the benzylic acid compound. Finally, the oxidation reduction reactions. These are very simple types of reactions. As you know, if you oxidize any aldehyde, you will end up with an acid. And if you reduce them, you will end up with an alcohol. So this is as simple as it is. In case of ketones, you can oxidize them using specific oxidizing agents such as conc nitric, and this will give an acid. And you can oxidize them using a very selective oxidizing agent. It's a name reaction known as the Baeyer-Villiger oxidation. How do we perform this? We add a peroxy acid. It's a regular acid but having an additional oxygen. This additional oxygen will just go in between the carbonyl and one of the R groups attached to it. Which R group? It has an order of priority. A proton is preferable to the phenyl group, preferable to the tertiary, then the secondary, then the primary groups. What does that mean? It means that if you have, for example, acetophenol and you perform the Baeyer-Villiger, your oxygen has now two choices. It can go between the carbonyl and the methyl and between the carbonyl and the phenyl. As we said, the proton is better than the phenyl, better than the tertiary, better than the secondary, better than the primary. So we have here the phenyl, it comes immediately after the proton, and on the other side it's the methyl that comes after the primary. So the oxygen will go in between the carbonyl and the benzene ring, giving an ester. The final product of Baeyer-Villiger is an ester. Let me remind you with a test that you performed in the lab, which was an oxidation reaction of aldehydes. If you remember, only aldehydes were capable of reacting with phthalate, changing its color. This is because phthalate is a mild oxidizing agent, and accordingly it oxidizes only aldehydes into acids. How is this useful? It's useful if you have any group that you fear for in your side chain. Instead of using non-selective oxidizing agents, you can just use phthalate so that your side chain stays the same, unaffected, and your aldehyde only is oxidized into the acid. Another reagent well known is the Thalen's reagent. Thalen's reagent is what is known as ammoniacal silver nitrate. While phthalate is phthalate A and phthalate B, phthalate A is copper sulfate and phthalate B is Rochelle salt in alkaline medium. So now if we again summarize the oxidation reactions, we have the non-selective oxidizing agents like permanganate or dichromate, and these oxidizes aldehydes into acids. And we have the nitric acid that oxidizes ketones into acids. We have the mild oxidizing agents like thalens and phthalate. These are mild and they only oxidize aldehydes into acids. Finally, we have a selective oxidizing agent of ketones, which is the Baeyer-Villiger oxidizing agent, where we use peroxy acid. Now we move to the reduction reactions. As we all know, if we reduce an aldehyde, it will be converted into the alcohol. What are the reagents that we can use? We can use all the metal hydrides. You can use lithium, aluminium hydride, or you can use sodium boron hydride, or you can use the regular catalytic hydrogenation. Okay, in case of ketones, you can reduce them by a non-selective reducing agent, ending up into the secondary alcohol, or you can use something more specific like the Merwin-Pendorf reducing agent. What is the Merwin-Pendorf reaction? It's the exact opposite of the Oppenauer oxidation. If you remember, in the methods of synthesis of ketones, we had a selective oxidizing reaction, which was the Oppenauer, where we used a secondary alcohol, any secondary alcohol, and we added acetone to this alcohol in presence of aluminium tertiary butte oxide. The product was an exchange between this carbonyl and the alcoholic part, giving the ketonic compound. Merwin-Bundorf is the exact opposite of this compound, of this reaction. You will start with the ketonic compound and you will add isopropanol to this compound in presence of aluminium. So you end up with aluminium tertiary butoxide. The end product is that the OH is exchanged by the carbonyl and you get the secondary alcohol together with the acetone molecule. So they are opposite to each other. Finally, we have one last type of oxidation reduction reactions. It's a reduction reaction. If you remember, we have what we called Clemmensen reduction. Remember them? And the Wolff-Kishner reduction. The Clemmensen was a reaction where you used zinc, HCl, and mercury. And the Wolff-Kishner, you used hydrazine in presence of sodium hydroxide, and in both cases you converted a carbonyl into a CH2. So you were converting carbonyl compounds into alkanes. If we look at the organized slides, as we said, we have oxidation reduction reactions of aldehydes, where you can use strong oxidizing agents giving the acid. And in case of ketones, you can use conc nitric giving the acid. We have mild oxidizing agents like toluenes and ammoniac and Fehling. Toluenes is ammoniac and silver nitrate, and Fehling is Fehling A and Fehling B. And these only oxidize aldehydes into carboxylic acid, and it does not affect any group in the side chain. We have a specific oxidation reaction of ketones that will not affect anything in the side chain, giving an ester, where we use the pair acid. It introduces an oxygen between the carbonyl and one of the R groups attached to it, and this is the order of preference of the oxygen to move to. We have the reduction reactions, and as we said, we have a very selective reducing agent, which is the Merwin-Bundorf-Varley reduction, which is the opposite of Oppenauer oxidation reaction, where we use a ketonic compound with isopropanol in presence of aluminium. The end product is that the carbonyl compound will be converted into the secondary alcohol, and the isopropyl alcohol will be converted into acetone. We have the regular reducing agents, which are the metal hydrides like lithium aluminum hydride and sodium boron hydride. They give the alcohol, whether primary or secondary. And we have the catalytic reduction, but remember that if you perform catalytic reduction using high temperatures, you will reduce the carbonyl compound together with anything in the side chain. However, if you perform this reaction at only 25 degrees centigrade, you will retain anything in the side chain. It will be selective only to the aldehydic group. The product is missing a double bond here, so the double bond will not be affected. This double bond stays unaffected if you perform this reaction at 25 degrees centigrade. Finally, as we said, we have the Clemmensen reduction and the Wolff-Kishner reduction, where we reduce a carbonyl into a regular alkane. In case of Clemmensen, we use zinc, HCl, and mercury. In case of Wolff-Kishner, we use hydrazine in presence of sodium hydroxide. This way, we have ended the aldehydes and ketones in 3 videos. Part 1 dealt with the structure, synthesis, nomenclature, and physical characters. Part 2 dealt with the first 2 types of reactions, which were the nucleophilic addition, and the second type is the condensation, where we first performed nucleophilic addition followed by removal of a molecule of water. The third video dealt with the second 2 types of reactions of aldehydes and ketones, and these were the reactions of alpha acidic hydrogen and the oxidation reduction reactions. The reactions of the alpha acidic hydrogen were three types. We had the aldol, the haloform, and the Mannich reaction, and we had some related reactions like Cannizzaro and benzoin condensation. And then we had the oxidation reduction reactions. First, the oxidation were the non-selective oxidizing agent like potassium permanganate and dichromate, and conchnitric in case of ketones. And then we had the mild oxidizing or selective oxidizing agents like toluenes and Fehling. And then in case of ketones, we had the Baeyer-Villicher as a selective oxidation reaction to only ketones, converting them into the esters. Finally, we dealt with the reduction. We had the Merwin-Bondorf, which was the exact opposite of Oppenauer. And we had the metal hydrides and the catalytic reduction of aldehydes and ketones. And finally, the Clemenson and the Wolff-Kishner reduction. So if we summarize aldehydes and ketones, we will have first the methods of synthesis of aldehydes and ketones. We have the oxidation, we have first the oxidation of alcohols into aldehydes and ketones. We have, in case of aldehydes, the PCC, and in case of ketones, any non-selective oxidizing agent, or we can use the Oppenauer oxidation. This was the first method. The second method was from alkynes. You can run a Markovnikov or anti-Markovnikov addition of water, which will end up into the aldehyde or ketone. Then the third type was the geminal dihalides, where you could perform nucleophilic substitution of the halogen using a hydroxyl group, giving the geminal diol, and then it is converted spontaneously into the aldehyde and ketone. Finally, we can convert acid derivatives like the acid halides and the esters into aldehydes and ketones. The acid halides, we have two methods, either the Rosenmund reduction or we have the dialkyl cadmium. In case of esters, we have the dibal as a reducing agent, or we have the Grignard as an organometallic compound, but we said that it's not preferable. So these were the methods of synthesis of these compounds, and don't forget the Friedel-Crafts acylation to give the aromatic compounds. These were the methods of synthesis of these compounds. Then we had their reactions. First was the nucleophilic addition reaction, where we added an alcohol to these compounds, giving the acetals and the ketals. We had addition of a Grignard reagent, giving alcohols, and we had addition of the cyano groups, giving the cyanohydrins. The second type of reactions was the condensation, where we condensed the carbonyl compounds with different amines, whether primary amines, secondary amines, or amine derivatives. And don't forget that amine derivatives had the oximes with their geometrical isomerisms, and they had the hydrazones that were used in the Wolff-Kishner reduction. Now, the third type of reactions is the reactions due to the alpha acidic hydrogen. And these were three types of reactions. These were the aldol condensation, the halogenation both in acid medium and in alkaline medium, and finally the Mannich condensation. Remember that we have a reaction related where compounds that do not have an alpha acidic hydrogen perform, like Cannizzaro and benzoin condensation. Finally, we discussed their oxidation reduction reactions. We said that the oxidation will be done using either non-selective strong oxidizing agents or mild oxidizing agents, which are selective only to aldehydes like Fehling and Tollens. And we have the famous Merwin-Bondorf oxidation reaction of Merwin-Bondorf. It's the not Merwin-Bondorf. It's the Baeyer-Villiger. Merwin-Bondorf is a reduction reaction. We have the Baeyer-Villiger oxidation, which is famous for ketones, converting them into esters. And then we have this is the oxidation, and then we have the reduction. We have the Merwin-Bondorf. We have the metal hydrides, and we have the Clemenson and the Wolff-Kishner reduction. This is how we can summarize this class of compounds, the carbonyl, aldehydes, and ketones.